So that specific atom is the atom that gets attacked by the benzene ring. So remember, you're taking that general mechanism and applying it. So I'm just going to show you what the electrophile is. And so then for our benzene sulfonic acid, I'll draw it over to the side here. We have our sulfur, 3 oxygens. So it's a double bond, another double bond. Hold on, let me redraw this. A little lower. All right. So we have our sulfur, double bond to oxygen, another double bond to oxygen, single bond to oxygen. Those are our 3 oxygens, and then a hydrogen on there. So this is our group. And so with this sulfonic acid group, this is what's called a director. It can direct other electrophiles to the benzene ring. So we'll see this in the next chapter. What I'm telling you about right now will come up more in the next chapter. So with this, though, if you want to use it to direct electrophiles to other positions, then after you finish those reactions, then we can remove this group. So it's a directing group, a blocking group. You can remove it by reverse sulfonation. So here's the reverse sulfonation. We have our sulfonic acid group. We remove it by acid and water, and we heat it. So another way to write this would be H plus H2O and then delta. Another way to write what's over that arrow. That is going to reverse that reaction. So this is our sulfonation, following the same mechanism as the other ones. All right, so then our next reaction comes from 15-11. So this is a name reaction. It's called Friedel-Crafts Alkylation. So we can have a haloalkane and benzene react, but they have to react in the presence of a Lewis acid catalyst. So usually we'd use like aluminum bromide or aluminum chloride. Remember, X is the halogen. And so what is reacting here? Well, we have our partial positive R group, whatever carbon is bonded to the halogen. And so we know that that's going to be the electrophile. Right? We've already been using this haloalkane carbon, whatever carbon is directly attached to the halogen. We've already been talking about that as the electrophile. It's the electrophile here. So you need catalytic aluminum halide. And then with that, you can do the Friedel-Crafts alkylation, where we add whatever that R group is to the benzene ring, whatever that alkyl chain is. So let's look at this reaction in a little more detail. So how reactive are those haloalkanes? Well, it depends on the polarity of the bond. So remember, fluorine is our most electronegative atom. And so with that, that's going to be the most polar bond. So it's also going to be the most reactive. So that RF is going to be most reactive. And then we have our bromine and our chlorine as kind of intermediate. We use aluminum halide, so usually aluminum chloride, aluminum bromide, but there are other Lewis acids that you might see. So boron trifluoride, this SbCl5 or FeCl3, so this iron chloride. But all of these are going to just be the Lewis acid catalysts used for the electrophilic aromatic substitution. They all follow that general mechanism. So you don't have to worry about using the aluminum chloride in your mechanism. Just have your carbon that has the partial positive, have that as your electrophile as you're doing that mechanism. So remember what an electrophile is, something with a partial positive or something with a full positive charge. So here it has a partial positive, so you know that that's your electrophile. And so then with numbering this, carbon 1, carbon 2, carbon 1 is bonded to the benzene ring because that was the electrophile. Carbon 2 is over to the side. So catalytic aluminum chloride, here we'll do this reaction. Questions on this so far? We can do an intramolecular Friedel-Crafts also. So here, partial positive, partial negative. That carbon, that's your electrophile, is far enough away that you can end up making a 6-membered ring. Remember, we can do intramolecular reactions as long as we can make a 5 or a 6-membered ring. So it's going to be a fused system. We have a benzene ring fused with this alkyl chain because we could make a 6-membered ring on the side of that benzene ring. So they're showing you this blue dot carbon. That's the carbon that was the electrophile. That ends up directly bonded to the benzene ring. Now, don't worry about this stuff over the arrow. They're just giving you the specifics for the solvents here for this specific reaction. But just note that it has what we know, which is catalytic aluminum chloride here. And then we make this product called tetralin. So for this reaction, we can use any kind of haloalkane, but we can't use aromatic or vinyl halides. So we can't have our halogen attached to another benzene ring. So we use one benzene and then this other one where we have a halogen. We also can't use vinyl where it's a double bond directly attached to this bromine. We can't do that because the corresponding cation, so here we would have to have, for this benzene ring, a positive charge on the benzene ring, or we'd have to have these two carbons where there's a positive charge on the double bond. These two are energetically inaccessible. What does that mean? They are unstable, high in energy. So these are not starting materials for the Friedel-Crafts. These are unreactive halides. So really you want to use one of your just straight carbon chains for this Friedel-Crafts alkylation. So you can have a benzene ring there somewhere else. So here's a benzene ring down in the chain, but it can't be your halogen directly attached to the benzene ring. So for this reaction, anything that can form a carbocation intermediate, that can be used for this reaction. So here we have an alcohol. And so we add in our Lewis acid catalyst here, boron trifluoride. And so with this alcohol, you know you would protonate the alcohol, and you have a good leaving group. What's your leaving group? Water. We've seen this reaction before. So water as our leaving group, we end up with this carbocation where here we can see our electrophile is that carbon with a positive charge. So if that's your electrophile, then that's the carbon that gets directly bonded to the benzene ring. Here we can do this reaction, the second reaction where we have HF. What would HF be used for? Well, we know we can protonate, and then we break that bond. So if we protonate, then one of those carbons of the double bond ends up with a positive charge. And so that carbon would be your electrophile. And so then you could do the reaction with this as your electrophile in order to make this product. So it might be a few steps in the process where you are making your electrophile, you're making your carbocation, and then with your carbocation, then the electrophilic aromatic substitution reaction takes place. So it might be a few steps in the process beyond just the mechanism for the electrophilic aromatic substitution. But again, this is stuff that you have seen before. Questions on this? All right, so with the Friedel-Crafts alkylation, we have a couple of problems. Here's problem number one. Problem number one is that when you're doing a Friedel-Crafts alkylation, you can go too far and do a polyalkylation. And so your yields will be lower for the product you want, the monoalkylated product, because you've added too many of these alkyl groups. So why wasn't this a problem before? Well, when we did the bromination, the nitration, and the sulfination, we were always introducing an electron withdrawing group. So we were having attached to the benzene ring, so we'll just call it R, where R could be bromine or chlorine, where R could be NO2, or R would be that SO3H. For all of these groups, these are all electron withdrawing groups. So once we form that compound with any of these groups as R, now the ring has lost some electron density. And so we would say this is deactivated for the electrophilic aromatic substitution. When you have a group on there, so let's say R is nitro, with that electron withdrawing group, it's pulling electron density out of the benzene ring, and so it's going to be a single substitution. But if we put an alkyl group on there, so here for this example, there's the isopropyl group on the benzene ring. With that now, we know this is an electron donating group. And so with that as an electron donating group, this ring is activated. When you have an electron-rich ring, it's activated for further electrophilic aromatic substitution reactions. And so it is easy for us to add a second or third or fourth alkyl group, so we can do over-alkylation. Because we have an electron donating group that we're introducing in our first electrophilic aromatic substitution reaction, it makes us more able to do further electrophilic aromatic substitution reactions. But if you have an electron withdrawing group, then that's going to kind of slow down the reaction enough that you can only do a single substitution. Questions on that? All right, so our second problem number 2 is that we can do rearrangements. So remember, we're making these carbocations, and we're using that as our electrophile. And so with these carbocations, what do we know about them? We know that they can do hydride or alkyl shifts. So if we had this starting material, so carbon 1, 2, 3, we would expect to get this product 1, 2, 3. We would expect this product. Only 6% yield of this where, okay, yeah, this carbon has a partial positive and bromine has a partial negative. What happens is that we do a hydride shift. You can see that hydride shift there. And so with the hydride shift, then our bromine can leave, where we end up with an isopropyl carbocation. So instead of having this carbocation, which we know is unstable, we have this carbocation. So instead of having carbon 1, 2, 3, carbon 1 being our electrophile, carbon 2 is our electrophile. And so carbon 2 ends up bonded to the benzene ring, 85% yield. So you get this unexpected product. If you want this product, you're not going to get it by doing this Friedel-Crafts alkylation. This product cannot be accessed through Friedel-Crafts alkylation. We'll see another reaction that how we can access this, but not through a Friedel-Crafts alkylation, because we would have to make the secondary carbocation, and that would be your electrophile here to make that rearranged product. Questions on that? All right, so that's our Friedel-Crafts alkylation. We also have a Friedel-Crafts acylation. Acylation. So what is an acyl group? An acyl group is just any kind of an R group, where R could be really a hydrogen or some kind of an alkyl chain. So that would be an acyl group. So with this, in this reaction, we have our benzene ring, we have this carbon that is a carbonyl attached to a halogen that reacts to make this carbonyl carbon bond for the benzene. We add an acyl group to the benzene ring. If we have that acyl group, if R is a hydrogen, then this would be called a formal group. And so the reaction would be called a formylation. Instead of an acylation, it would be called a formylation. If we added this, where R is just a methyl, this is called an acetyl group, so this would be called an acetylation. An acetyl group, so it would be called an acetylation. But in general, they're called acylations because we're mostly just adding acyl groups So in general, for this reaction, you're most likely just going to be making some kind of a ketone. There's only one aldehyde possible, and the only aldehyde possible is this one where it's a formal group. Anything else would be some kind of a ketone attached to the benzene ring. So how does this reaction occur? Well, we end up with, here we have this R group attached to a carbonyl with a halogen. And so what happens here is something weird. We don't usually see this. We would move these electrons down and have our leaving group leave, where we end up with this R group attached to a carbon that's in a triple bond to oxygen. And that oxygen would have just one lone pair on it. We know when oxygen has 3 bonds, it has a full positive charge. So we give it a full positive charge. Now, I've already set this up so that you can see that this has resonance where oxygen hates having that positive charge, so we can move those electrons back to our oxygen, where the carbon has a positive charge now. So you can see that for these resonance forms, the carbon ends up with a positive charge, which would make this our electrophile. And you could have it be the carbon in either one of these resonance forms. It doesn't matter. That carbon is electrophilic. And so this is going to go through what's called the acylium cation. Acylium cation here. That's what you see here below. RC with a triple bond to oxygen with a positive charge. This is our acylium cation. And with this is not prone to rearrangement. This can avoid rearrangements. Why is that important? Because we just talked about our Friedel-Crafts alkylations and how they will do rearrangements. So that's why Friedel-Crafts acylation is going to be superior to the alkylation. One reason, it's not prone to rearrangements. So let's look at the nitty-gritty of the reaction. When we have our benzene and our acyl halides, what's an acyl halide? Acyl with some kind of a halogen on it. When we have these reacts, we don't use a catalytic amount, we use a stoichiometric amount of the aluminum halide. So this is not a catalytic amount. We use a catalytic amount for the previous reactions, but when we're doing the acylation, we don't do a catalytic amount. We have to use a stoichiometric amount. So 1 to 1 or even 1.2 to 1, something like that. When we do this reaction, we also have an aqueous workup step, and we'll see why that's necessary, but it's a 2-step process where then we can add in our group here. Specifically, this is an acetyl group that we've added, and so we make acetophenone. With this, we have our acyl chlorides, but how do we make them? So how do we make our acyl chloride? We start off with a carboxylic acid. Our carboxylic acid reacts with thionyl chloride, SOCl2, and then we make our acyl chloride along with sulfur dioxide and HCl. So this is the reaction to prepare the acyl chloride, so make sure you know this reaction because that would be used to make our starting material in the electrophilic aromatic substitution. But there is an issue with this reaction. This sulfur dioxide is a toxic gas, and so doing this in real life, so like for my research, we need to do a reaction like this, but it's dangerous, and so I'm trying to avoid it in my research because we would make a toxic gas. That obviously is something difficult to handle just for undergraduate students especially. So I try to avoid the use of this, but if you need this acyl chloride, this would be how you do it, and you just have to take special steps to avoid inhaling that toxic gas. So for our reaction, we have the acylium ion as our electrophile. We use that to begin our mechanism for the electrophilic aromatic substitution. We said that the acylium ion is not prone to rearrangement, but now we need to talk about, can we do polyalkylations? This benzene ring is deactivated. It is deactivated for further electrophilic aromatic substitution reactions because it has this ketone on it. The aldehyde or the ketone on the benzene ring, you know that that's an electron withdrawing group. We already talked about this kind of stuff. Remember when we were talking about the Diels-Alder? Electron withdrawing group, electron donating group for the diene or the dienophile. Those same things apply here. So we have an electron withdrawing group that is going to pull away electron density, deactivating the ring for further electrophilic aromatic substitutions, which means we can avoid polyalkylations or polyacylations here. So that makes this superior to the Friedel-Crafts alkylation reaction. Questions on this? All right, so why do we have to use a stoichiometric amount of the catalyst? Why can't we just use a catalytic amount, a very small amount? We have to use a stoichiometric amount because our product, that acyl group, really likes aluminum. It really likes aluminum. So if you have a little bit of around, then the aluminum, instead of reacting with your starting material, it will react with some of the product that you make, forming this complex, Lewis acid complex here. So we have to have 1-to-1 or even a little bit of an excess of the aluminum chloride so that we can have enough of it around to react with our starting materials so that then it can do what it wants to do. This is just like we were talking about. Remember with our alkyne, and we use 3 equivalents of base because we said the base just wants to deprotonate the alkyne, the terminal alkyne. So we have to add in more base so that we can let it do what it wants to do. Aluminum chloride wants to complex with the oxygen. So we added more aluminum chloride so that some of it can complex with the oxygen and some of it can still be around to react with our starting materials. So with this complex, that complex would get removed in the aqueous workup step. The aqueous workup step will remove that complex, allowing us to go back to form our product. So that's why we have our aqueous workup step, because that is going to remove that Lewis acid so we can get our ketone or aldehyde if it's a formulation product. So notice the equivalence. So not a catalytic amount. Catalytic amount would be just some percent, like a mole percent of it, not 1-to-1. This is stoichiometric amounts of the aluminum chloride, and then we have to have a second aqueous workup step in order to get our ketone freed from the aluminum complex. So we can use an acyl chloride where we know our chloride is the leaving group. Or we can use anhydride. You saw anhydride this week in lab, right? We know what anhydride is. It's that group where you have oxygen in between 2 carbonyls, where we can have whatever on the end of the carbonyls, but this is called our anhydride. And so with the anhydride, everything that you see in green here, this whole thing is the leaving group. And so we add on this 2-carbon chain. Where that leaving group leaves, we get our acylium ion. So remember the ion, carbon with a triple bond to oxygen. We get this ion where we know we have this as our electrophile. So this is our Friedel-Crafts acylation. Here we're making an acetyl. Here we're just making a regular ketone. Questions on this? All right, so we talked about our Friedel-Crafts alkylation and our Friedel-Crafts acylation. We said the acylation is superior because we would get a single substitution. We've added in an electron withdrawing group, so we get a single substitution, and we don't see any rearrangement. So we can do this process. So we can start off here, and we end here with this alkylated benzene. So let's look at this process. The process here would be a two-step process in the beginning to the Friedel-Crafts Acylation. We have a stoichiometric amount of the aluminum chloride, and we know we need an aqueous workup step, but that allows for us to make our acylated product. So this is carbon 1, carbon 6, carbon 1, carbon 6. With this intermediate, we get a ketone intermediate. With this ketone intermediate, we can add in sodium borohydride. What is sodium borohydride going to do? Well, remember from last semester, it does a reduction, and so we can reduce the ketone to an alcohol. So we reduce that to an alcohol on carbon 1, and then we can do this second step. So remember section 9-2 in the textbook? So from last semester, we talked about with an alcohol, the alcohol can be protonated, right? We have a nucleophilic strong acid. So we protonate the alcohol. We get a good leaving group. And then we can use our bromide as a nucleophile. This is all from section 9-2. If you don't know what I'm talking about, go back and review. This is when I say this class is cumulative. This is what it means. Everything that we learned last semester, it's going to come up again in one way or another. So we end up with this halogen now on carbon 1. So then with our halogen, we can add in lithium aluminum hydride, or LaH. So we use sodium borohydride, hydride equivalent, to do that reduction. Lithium aluminum hydride, also a hydride equivalent. Remember what hydride is? Hydrogen with 2 electrons on it, with a lone pair, with a negative charge. And so what's happening here in this reaction? We can have our hydride attack carbon 1, and our leaving group leaves, right? This is a good nucleophile. And so if that attacks carbon 1, we end up with 2 hydrogens there. We've reduced that all the way to an alkyl group. So this is on the next slide, actually. The hydride equivalents are used to change that halogenated alkyl group into that alkyl group. And so we end up with a product that's an alkylated benzene. So we get a hexyl, 6-carbon chain on the benzene. If we had tried to do the Friedel-Crafts alkylation, we would have gotten this product along with the polyalkylation and carbocation rearrangement products. We would have gotten a big mess of products. We would not have gotten the hexyl benzene as the main product. So here we're doing a multi-step process, not using the alkylation, but using the acylation instead. Friedel-Crafts acylation instead of the alkylation, which allows us to get a high yield of the product that we desire, the hexyl benzene, rather than having the polyalkylated product or the product from carbocation rearrangements. Questions on that? So Friedel-Crafts acylations are more desirable than Friedel-Crafts alkylations, which you can get the alkylation product through an acylation and these further steps. All right. So we've started talking about our reactions with benzene. So really we've done just a few reactions here. We talked about how this reaction would be very slow. But then we talked about our halogenation, our nitration, adding in some kind of an alkyl group there. We also talked about doing our Friedel-Crafts acylation there with the acyl chloride and with the anhydride. So we have a few reactions that we discussed here. We're going to look at some more reactions in the next chapter, but we're not going to get to every single reaction that you see here. Some things we've skipped. Actually, we did look at these two as well. Anyway, all right, moving on to our learning checks. All right, so any questions before we begin our learning checks? All right, so for this first problem, we want to write the IUPAC name and any common name for the compound. So two benzene rings fused together, you just have to recognize that as naphthalene. And you know that you could draw it like this, where you have the circle in there. That's fine for both of those. That's totally fine. All right, there's no common name for that. That's just called naphthalene. So that's the IUPAC name for that. Now let's look at our next one. So we have a fluorine, so a fluoro group, and then NO2, which is a nitro group. We have it as a disubstituted benzene ring. What's going to be on carbon 1? The fluoro has to be on carbon 1 because we're basing it on alphabetical order. We have a tie between what's on carbon 1, what's on carbon 3. So on carbon 1, we have the fluoro. On carbon 3, we have the nitro, and it's a benzene ring. Now we can do a common name here. So remember, we talked about our common names, ortho, meta, and para. So here we can see that that's an M, so meta. You can just write M, or you can write out meta. And so meta means 1, 3. So we don't need to have a number. We just write fluoro, nitro, benzene, all one long word. The meta means 1, 3. Questions on these two? All right. Again, IUPAC and any common name for these two. All right, so we want to have it as the lowest number possible first off. That's our first rule. Then we break the tie with alphabetical order. We want to have our lowest numbering possible. So our lowest numbering possible, it doesn't matter what anything is called here. Your lowest numbering possible is a 1, 2, 4. Then you put the groups in alphabetical order. So 1, 2, 4 is the lowest number possible, alphabetical order, 2 bromo. 4, what is this? An ethyl plus an oxygen, eth-oxy. So 4 ethoxy, 1 methyl, benzene. Can we do a common name here? Yes, we can. So for the common name, we have to remember that this is called toluene. And toluene is acceptable for IUPAC. Sorry, for common, not for IUPAC. And so if that's toluene, then this has to be carbon 1 if we were numbering it for the common name. It is carbon 1 for both, so we're fine there. But if we're calling it a toluene, then that methyl would have to be on carbon 1 for the common name, but we're fine. So the common name is 2 bromo, 4 ethoxy, and then instead of 1 methyl benzene, toluene. So again, because we're calling it a toluene, that methyl has to be on carbon 1 for the common name, but it is carbon 1, so we're fine. And then we just call the rest of it a toluene instead of a methyl benzene. All right, for this one, we have a 1, 4. Which one is going to be on carbon 1? We have a tie. So we have a propyl, 1, 2, 3, and then here we have 2 methyl propyl. M versus P. So we know which one is on carbon 1. We know which one's on carbon 4. So here the name would be 1, 2 methyl propyl, 2 propyl, and then benzene. Can we do a common name here? Well, yeah, we can do ortho, meta, para. Remember para, parachute. You want your parachute as open as possible. So 1,4, that's a para relationship. But also remember that when we have our common name, we can change up the names of these to those alkyl names that we learned last semester. So this is called an isobutyl. 4 carbons, and we said it looks like isopropyl, right, where it has that V on the end, but it's isobutyl. For that, I is alphabetical order. So isopropyl, propyl, benzene. Questions on these two?
Quick question. Didn't you just say that it's supposed to be isobutyl?
Oh, sorry. I said isopropyl, but because I was talking about the isopropyl. Questions on that? All right. Oh, go ahead.
Do you capitalize the P or the M or the
No,
O?
they are lowercase. All right, so these are going to be ones that you should just recognize. So remember we talked about, we had that table, and I said these are the ones you need to know, and you need to know these that are acceptable for IUPAC and common. So make sure you know those things because you need to just recognize it. If you have to look this stuff up, it's going to take you a lot of time on your exam. So for this, you should just recognize this first one as methylbenzene and as toluene. For the second one, 2-carbon chain, no number needed in the beginning if there is only one thing attached to the benzene ring, and no number needed for your substituent because there are only 2 carbons in that substituent chain. So no number needed for where the double bond is, and no number needed for where the substituent is. So we just call this ethynyl benzene. But you need to recognize that this is styrene for the common name. Styrene for the common name. So remember, styrene is used to make styrofoam. This is the monomer used to make the styrofoam polymer. Okay, then the other two that were on this same slide, here we have a dimethyl, so 1,3. It doesn't matter which one's on carbon 1, which one's on carbon 3, because they're both the same thing. But you have to recognize this as, first of all, meta. And then also, this has another name. When you have those 2 methyls on the benzene ring, that's called xylene. So meta-xylene. Then we have here a benzene ring with OH on it. So you need to recognize that as phenol, and phenol is acceptable for IUPAC and common. Phenol is acceptable for IUPAC and common. The solutions manual might write benzenol, but ignore that. Write phenol instead. We're going to write phenol as IUPAC and common. Questions on these 4, so on the previous slide or here? All right. Any questions on these? All right, then let's do another, write the IUPAC name and any common name. So looking at this, we have a benzene with an amine. And so this is called an amino group. You've heard of an amino acid, right? An amino acid has some kind of a nitrogen on it, and then it has a carboxylic acid. So here's the amine. So the IUPAC name for this would be benzene, but drop the E, and then put amine. Benzene, drop the E, and put amine. So benzenamine is the IUPAC name. But the common name for this is aniline. Aniline. All right, then our next one, we want to give this the lowest numbering possible, so we know that'd be a 1, 4, but we have to recognize that this is called benzoic acid. And so if this is benzoic acid, that's acceptable for IUPAC and common, so that has to be carbon 1. The whole thing is called a benzoic acid, not a benzene here. So if the whole thing's called a benzoic acid, then this would be called 4-bromo benzoic acid. Benzoic space acid. Can we do a common name? Well, yeah, this is para disubstituted, so para-bromo benzoic acid. Para-bromo benzoic acid. Questions on these two? All right. Now we have 3 things attached to this benzene ring. We said we would give it the lowest numbering possible, but we have another one of our acceptable for IUPAC and common groups. This is called, we have an aldehyde here, benzaldehyde. You have to just recognize these so you can give them the right name possible. And so benzaldehyde also acceptable for both. So this has to be carbon 1. So then you give everything the lowest number possible based on that being carbon 1. So if that's carbon 1, the lowest numbering possible would be this being 2 and this being 5. So our IUPAC name there then would be, alphabetical order, 2-iodo, 5-methyl, and then benzaldehyde. Not benzene, but benzaldehyde. Can we do a common name here? No. There's no common name. So here's why there's no common name. We can't do orthometapara. There is no way for us to do a common name. I guess I should say no new common name for the benzene ring. And the other thing, no orthometapara. Oh yeah, then we can't do one of our like isopropyl, sec-butyl, one of those. We don't have one of those branched alkyl names. Those would be the ways that we could do a common name. All right, let's look at this next one. Here we have benzene ring with an OH. We have to recognize that as phenol. So this has to be carbon 1. This has to be carbon 2. Phenol is acceptable for our IUPAC and common. So if it's acceptable for our IUPAC and common, 2-ethyl Phenol. Common now, we can do orthometapara, so ortho ethyl, but it's still called phenol. Questions on these two?
Is that all one word for the ethyl phenol?
Yes.
Or one's a space?
No, it's all one word.
Okay.
Professor, so
Yeah.
for like these, do we have to like okay, I understand you're giving us both the I and C, but when I was doing the homework, I saw that like they have different ways of naming it. They're giving me like three, four options for some questions. So yeah, some of them like
Bring that up in office hours and show me the example.
okay,
Talk,
okay.
talk to me about what you are talking about specifically. Let's see here. So what about this compound? How would we name this? So all I did was change this methyl to an OH. Is this a phenol or is this a benzaldehyde? Which one is higher priority? If they're both there, we look for the group that has the higher priority. And so what is the higher priority? More bonds to oxygen. So what is higher priority here? Benzaldehyde. And so we don't name this as a phenol now. Now this is called a hydroxy group. And so the IUPAC name would be, so hydroxy for alphabetical order comes first. So 5-hydroxy, 2-iodo, and then I need to go down to the next line. That's the only reason this dash is here, because I need to go down to the next line. But if you don't, then make it all one word, iodobenzaldehyde. But I ran out of space there. So that would be that IUPAC name. And again, no common name. Oops, none. All right, so when there's a higher priority group, 2 bonds to oxygen versus 1 bond to oxygen, then it gets named as the group that has more bonds to oxygen. Questions there? All right, now we're thinking about Huckel's rule. Remember Huckel's rule helping us figure out if this is aromatic, anti-aromatic, or non-aromatic? So first thing we need to do is assume that all of these are planar other than the one that we write that I tell you is non-planar. All right, so they're all planar. They're all cyclic. Now we need to know how many pi electrons. So pi electrons, remember in the double bonds, those are our pi electrons. So how many pi electrons do we have for this first one? Anybody put that in the chat, please? For this first compound, how many total pi electrons do we have here? We have 14 pi electrons. And so with 14 pi electrons, is that 4n plus 2 or is that 4n? It's 4n plus 2. Why is that 4n plus 2? N would equal 3, right? 4 times 3 is 12, plus 2 equals 14. So this would be 4n plus 2. When we have 4n plus 2, and it's planar, and it's cyclically conjugated, everything is double, single, double, all the way around. This is aromatic. Conjugated all the way around all of the rings, 14 pi electrons, planar, 14 aromatic. All right, how many pi electrons do we have for this second one? 4. So 4 pi electrons, this would be 4n. This is conjugated because of the positive charge. It's conjugated because we can draw all these resonance forms. Without the positive charge, this wouldn't be conjugated cyclically. So it wouldn't count. It would be non-aromatic. But because we have that positive charge there, we can draw different resonance forms for this. So this one is anti-aromatic. Let's look at this next one. Double, single, double, all the way around. There is no double, single, single, I should say. So it's cyclically conjugated. It's a ring. How many pi electrons here? I'll just tell you, yep, 14. So 14 pi electrons, another 4n plus 2, aromatic. Now look at this next one. Double, single, single, double. The other direction, double, single, 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 double. It's not conjugated, and it would have to be conjugated all the way around the ring. It's not conjugated cyclically, and so this would be non-aromatic. You need to have cyclic conjugation everywhere around the ring, or a positive charge or a negative charge that will allow you to do all these resonance forms, so non-aromatic. And then non-planar, also non-aromatic. It doesn't matter about how many pi electrons it has. It doesn't matter that it's cyclically conjugated. If it's non-planar, non-aromatic. Questions on these? So you have a slide in your notes that summarizes everything that I'm doing here. So if you're confused, that's because you didn't go back and review your notes. Not to say don't ask a question, but just to say, like, if you're like, where are you getting any of this from? It's in the slides. But do you have a question on this? All right, let's go on. So here's our electrophilic aromatic substitution reaction. HNO3, nitric acid, H2SO4, we know we're going to make. These are so easy because all you have to do is add in the group that is required. This would be an NO2 group. So think about the intermediate that you would need to go through from this, what that would make to make the electrophile. But you make nitrobenzene here. SO3, H2SO4, fuming sulfuric acid. Okay, what's our product? SO3H. HNO3 turns into NO2. SO3 turns into SO3H. This is called benzene, keep the E, sulfonic space acid. Questions on that? We're going to add on to these in the next chapter, so we're kind of laying the groundwork here with what we're learning. All right, here's a chlorination. So what's our product? Chlorine being added here. You need to know the mechanism, but this is our product. If we have chlorine and we add in magnesium metal, we know this reaction, we've been doing it for forever. We're going to make a Grignard. So we turn our partial positive carbon into a partial negative carbon. If we have a Grignard and we react it, middle of the bond to our electrophilic carbon here. We know we push electrons up. Let's number this. We'll call this 1. I'll call this 2, 3, 4, 5. Then I'm going to have a benzene ring where carbon 1 is bonded to carbon 3. 3 is bonded to 4 and 5. Right? That's the bond I'm making. That's the arrow I drew. 3 now has carbon 2 on it, and we have an OH. You know this reaction. You've seen this a million times before. All right, that's where we'll stop. If you came in late, ask your lab partner what the surprises were today. Lots of surprises. Ask your lab partner, though. Check in with them to see what I said. But anyway, I'll see you guys for office hours. Have a good weekend. I love you. And I will see you on Monday for lecture.
Thank you.
You're welcome. Bye, you guys. Have a great day. Any questions before you guys leave?